History and basic information. The electron, debatably the most interesting and complicated part of the atom. The electron was first discovered in 1897 by English physicist J.J. Thompson. By this time, physicists and philosophers had already theorized the existence of the atom since 400 BCE. Thompson suggested that atoms are tiny positively charged spheres that contain negatively charged particles inside. He concluded this from his cathode ray experiments, noting that atoms would be attracted to positively charged plates. His conclusions, or the Plum pudding model, we now know is not true. After years of experiments and theories, we eventually narrowed it down what the electron is. This model, the Schrodinger model, shows where the electron, a subatomic particle or wave, has been and where it is likely to be. Where the electron cloud is densest is where it is most likely to find an electron at any given time. Schrodinger's equation is based on the idea that you can't determine the exact location and velocity of an electron, but only a field of probable locations. His theory is connected to the Heisenberg uncertainty principle, and that because of this principle, you can never have the exact location of an orbital. In electron shells, there are different levels of energy, from level 1 to level 7. Within these electrons' energy shells, there are different orbitals that an electron can exhibit, and each orbital can hold 2 electrons. Orbitals come in different shapes and sizes. The S-type orbital is shaped like a sphere orbiting around the nucleus. There is only one S-type orbital in each energy level, so each energy level contains 2 electrons in the S-type orbital. The P-type orbital has a dumbbell shape. There are 3 p orbitals in each energy level. With each orbital holding 2 electrons, in each level there can be 6 total electrons in the p orbitals. The d orbital has a clover shape. There are 5 d-type orbitals in each energy level, coming to a total of 10 electrons in the d orbitals per energy shell. Finally, we reach the f orbitals, an 8-lobe shape. There are 7 possible f orbitals per energy shell, coming to a total of 14 electrons in the f orbitals per shell. Valence electrons and the octet rule. It is because of these orbitals that each energy shell has a specific max number of electrons per energy shell. Atoms start out with a 0 charge. Their number of electrons equals their number of protons. Despite this, atoms always want to have 8 electrons, no more, in their outermost shell. This is known as the octet rule. The amount of valence electrons, or those in the outer shell, can be as simple as finding the element of your desire on the periodic table and looking at the handy-dandy group number, which tells you the number of valence electrons. If you're stuck with a transition metal, all those in the middle, simply write out the electron configuration and count up the number of electrons in its highest energy shell. Electrons and light. Electrons are also the origin of all the light and color around us. We start with just some electrons chilling in whatever energy shell they're currently in, but when these electrons are excited, whether through cathode ray or flame, they move to an excited state. This causes them to jump one or more shells out, absorbing energy. When they move back to their ground state, they release this energy in the form of a photon. The energy of this photon is calculated using Planck's law. The wavelength of this photon is what decides the type and color of light. Light can be visible or invisible, such as infrared. On the light spectrum, you can see the direct correlation between wavelength and light color. Periodic trends. The number of valence electron is not the only pattern you can find on your periodic table. Atomic radius, as I'm sure you've guessed, is the radius of an atom. The atomic radius is affected by the number of electrons. When there are more electrons around the nucleus, the atomic radius increases due to shielding. Shielding is when the inner electron shells block the nucleus from its outer shell. So as we go down the periodic table, the atomic radius is increasing. As you go across the periodic table, the atomic radius decreases. When there are more electrons in the outer shell without it becoming a new shell, the nucleus can pull in the outer shell. This pulling in decreases the atomic radius. Electronegativity is the energy that an atom holds shared electrons to itself. It's essentially how badly this atom wants that electron. For example, if we have the lovely H2O molecule, the bonded electrons will spend a greater amount of time near the oxygen atom than the hydrogen atom due to the oxygen's higher electronegativity. As you go across the periodic table, the electronegativity increases due to it being closer to the ideal 8 in its valence shell. However, as you go down the periodic table, electronegativity decreases due to the atoms becoming larger, so it is harder for the nucleus to pull in these electrons. The exceptions are the noble gases, the furthest column. These elements already have the ideal electron configuration, so they don't pull any more electrons in. The highest electronegativity is fluorine, with runners-up chlorine and oxygen. Ionization energy is the energy that it takes to remove an electron from an atom. Atoms with less electrons in the valence shell have lower ionization energy because the nucleus doesn't have a strong attraction to those outer electrons. So as you go across the table, ionization energy increases as the nucleus gets a better grip, making it harder to steal the electrons. While as you go down the table, ionization energy lessens as atoms get larger and have a weakened grip. Electron configuration is the recording of electrons found in an atom's orbitals, their behaviors, and the rules they follow. This is all shown in a visual or formula. The orbitals fill in a specific order, as seen in this diagram. First, the s orbital in energy level 1 is filled, then the s orbital in the second energy level, then the p orbitals in the second energy level, and then so on. You'll recall each type of orbital holds a specific number of electrons in the energy shell, and the beginner's diagram can show that. Let's say we have zinc, found here on the periodic table. Zinc has 30 protons, so when it's neutral, it will have 30 electrons. We start out with our 1s and add 2 electrons, opposite spin because electrons always want to be as far away as possible. We then move on to 2s and fill that. 2p has 3 orbitals, so it holds 6 electrons. We fill it in this order to show Hund's rule, that orbitals fill with 1 electron in each before pairing. 3s, 3p, 4s, and finally 3d, which has 5 orbitals, 10 electrons. All of these can be simplified into the equation 1s, 2s, 2p, 3s, 3p, 4s, 3d. Once you get used to how orbitals work, you can jump right to this equation by writing out 1s2, 2s2, 2p6 until the exponents, the number of electrons in that orbital level, reach the desired number. Looking at the highest energy level, in zinc's case 4, we can also conclude the number of valence electrons, 2. This will come in handy when you work on covalent and ionic bonds, but that's for another day. Thank you for watching. If you need more help in chemistry, look for future videos on this channel or any of these channels featured here.